This week we're going to start our discussion on hypothesis testing. I broke this into 2 weeks so that we can get a real grasp of what hypothesis testing is before we actually work on the calculations. Most of the calculations will be done in the calculator, and remember that on our front announcement page there is a link so that you can download your own calculator. That will be helpful for this chapter. We have in years past, in fact a very recent past, done hypothesis testing by hand using tables and comparing z-scores. But the calculator does that for us, and so we will rely on that kind of prop. Use our resources, right? So what is hypothesis testing? Well, we come up with two ideas in hypothesis testing. One is the status quo, and the other is, no, we think that it's going to be greater than the status quo, or less than the status quo, or even different than the status quo. And so we have some steps we're going to go through for this, and one is to set up these two contradictory hypotheses, or hypotheses, and then collect the data, and then determine in a distribution, our normal distribution, we're going to conduct this test and determine by analyzing the data if the calculations show that we should reject that null hypothesis, the one that is a status quo. If we should reject that and say, no, it really does show that it is a larger amount for the mean or a smaller amount for the mean or different, whatever we set up as the hypotheses. Then we have to make a decision and write that conclusion out. So it's not just the end when we do the test and we say, yep, that's it. No, we actually have to draw a conclusion. So that means that, and then use our inferential statistics and language for that. So we're going to, these two hypotheses that we're going to set up, one is called the null, and that's the status quo, and the other one is the alternative. In some books this is labeled H with a 0 by it for null and H1 for the alternate, and sometimes it's labeled HA. I think in this book it is HA. Yep, that's right there on the screen in front of me. But if you see H1 written, that means exactly the same thing. So these two hypotheses are statements about this population. The H0, the null hypothesis, is really where we are. We have to prove that it's different. So like I say, that one is a status quo. The other one, we actually have to have a lot of proof. So it is the alternate. We claim that the population might be contradictory to what our HO says. Since they are two opposite, we have to look at the evidence and decide. And this evidence would be in the form of data. So there's some things to remember about our hypotheses. And after, I think I will slide this down a bit so that you can see the very end, because that is really a little bit important right there. These two hypotheses, okay, they're opposites, right? So they are mutually exclusive and collectively exhaustive. There are not going to be any other options. Let's pick something simple like, I think that the mean of this thing that we've always thought the mean was 10. I think there's evidence to show that it is different than 10. It might be less, it might be more. It was just different than 10. So our null hypothesis would be mean equals 10. That is our null hypothesis. And our alternate hypothesis is that mean is not equal to 10. So in those two groups, there are going to be every other single number, right? You either are equal to 10 or you're not equal to 10. It is mutually exclusive and collectively exhaustive. The null hypothesis is always presumed to be true. We have to prove that the other one, the alternate hypothesis, has the burden of truth. And here we have the H1 symbol. Again, in your book, it's HA. So a random sample is used to reject. That's the only option we have, either reject or not reject. Okay. If we conclude do not reject our null hypothesis, that doesn't necessarily mean that the null hypothesis is true. It just means that we haven't shown enough evidence that we can reject it. So equality is always going to be part of that null hypothesis when we write them. It is always going to have the equal sign, whether it's part of a greater than or equal to, or less than or equal to, or just plain equal to. That is always part of the null hypotheses. The alternate hypotheses are never going to have an equal sign in them. So it is either going to be not equal to, or greater than, or less than. we're trying to disprove with that alternate hypothesis our null hypothesis. Our null hypothesis is what we're saying is equal, is true, is right now. Okay, that's status quo. And we're trying to prove the other one by data. There's no good place for my head in this one. Right here. So after you've determined which hypothesis the sample supports, then you make the decision. And there are two options for the decision. The option is to reject or to not reject. That's all we have. And here we just have a little chart that reminds us about that equal sign. It is part of the null hypothesis always. It is never part of the alternate hypothesis. And we probably are going to say the same thing, I don't know, another dozen times at least, right? Because that's kind of the way we teach things. I'm going to raise this just a bit. Okay. So since the null hypothesis always has a symbol with an equal sign in it, just always. I like things that are always, evidently. I do because I like math, right? And the alternate, it's never going to have the equal sign. So the wording is very important when you read some of the problems. How to put that into symbols is sometimes a little tricky for students. And we want to show some examples for this. There's a bunch of good ones in the book, but let's look at example 9.1 here. So we are reading this and we want to, we are claiming no more than 30% of registered voters in Santa Clara County voted in the primary election. So we are having that equal sign, no more than 30%. And this is the symbol that we would have for that, right? No more than 30% means less than 30%. And so we always have the equal sign because it's a null hypothesis. And our alternate is that more than 30% registered. So we would have it without the equal sign and just have the inequality symbol. Just some ideas of keywords and what they mean and what that would then mean for the hypothesis. Just some keywords. Sometimes you go over these in math classes, which this is, but in algebra classes, I guess I meant, where you're looking for what kind of words in a word problem mean certain symbols. And this is just a handy chart, excuse me, to let you know that. This other example, we want to test whether the mean height of 8th graders is 66 inches. Right there you can kind of see it's going to be our equal sign, right? So state the null and the alternative hypotheses. So our null hypothesis is going to be equal, and our alternate one is going to be not equal, because that is exactly what we're proving. Example 9.3, we want to test college students. If college students take less than 5 years to graduate from college on the average, the null and alternative hypothesis are, remember we need that equal sign with our null hypothesis, is that it takes college students, our mean, is greater than or equal to 5. We want to test, let's read the words again, we want to test if college students take less than 5 years. That is kind of the alternate thing that we're talking about. So our status quo is that it takes them more than 5 years or equal. Okay, so that's where our equal sign is. And then our alternate would be less than 5 years. Here's another one. Move my head up a little bit. In a report, an article on school standards stated that half of all students in France, Germany, and Israel take advanced placement exams and a third pass. The same article stated that 6.6 of U.S. students take advanced placement tests and 4.4 pass. Test if the percentage of U.S. students who take advanced placement exams is more than 6.6%. State the null and alternative hypothesis. So here we see it is stated that it is 6.6. I want to see if with the data we can show that it is more than 6.6. So my null hypothesis is that it is not more, right? Status quo is that it is equal to or less than 6.6% or 0.066. And then the alternate hypothesis would be that it is more. That is what we're trying to prove. Burden of proof is always with our alternate hypothesis. 9.4, on a state driver's test, 40% pass the test on the first try. We want to test if more than 40% pass the test. So our alternate hypothesis is not going to be more than. It is going to be less than or equal to. and our alternate hypothesis is more than. That is what we're trying to prove. There are errors associated with hypothesis testing, type 1 error and type 2 errors, because the data might show something that actually might not be true. So we have type 1 error and type 2 errors here. And just reading through what a type 1 error is, it's the probability of rejecting the null hypothesis when it is actually true. So we do the data, we do the calculations, and we reject the null hypothesis where really it might be true. Maybe we didn't use enough data. Could be lots of reasons. And this is denoted by the Greek letter alpha. It is also known as the significance level of a test. So we want to have this level be very small, right? To have that level of error small. A type 2 error is defined as the probability of failing to reject when it is actually false. So the data shows that that we should reject, and we don't reject. We fail to reject. It shows that we should reject the null hypothesis, but really we should not reject, failing to reject the null hypothesis. This kind of error is denoted by the Greek letter beta. So just some ideas of how that works. You'll see that in your book. Go ahead and, as you're doing your reading on these sections, I think we go through section 9.3. We start 9.4 for next week's lesson. So we're just really understanding how to write these, what they are, and we will get more into actually doing the testing of our hypotheses in next week's assignments. Thanks.